The molecules that we've talked about so far have not had any lone pairs on the central atom, but some molecules do. So if there are lone pairs, then it gets a little more complicated. And now we refer to two types of geometry. There's the electron geometry, which is the arrangement of the electron groups. And then there's the molecular geometry, which looks only at the arrangement of the atoms. So if you have no lone pairs on the central atom, electron geometry and molecular geometry are the same. So let's look at ammonia. So I'll draw the Lewis structure here real fast. We look at the Lewis structure and we count the groups, and there's a lone pair is one group, and a bond is one group, and another bond and another bond, so 4 groups. 4 groups make a tetrahedron. So the electron groups make a tetrahedral shape, okay? How do we determine the molecular geometry? Well, I like to think of any lone pairs as being invisible balloons, right? So here we made this shape with our 4 balloons for our 4 electron groups. But now the one that's a lone pair, we're going to pretend is invisible. It's not that it isn't there, it's not that it goes away, but we can't see it. Poof, it's gone. It's just invisible. And the molecular geometry is describing the shape that the atoms make. So the hydrogens are making a triangle, but the nitrogen is not flat down in the same plane. It's sticking up a little bit. And so that's called a trigonal pyramid or trigonal pyramidal geometry. The words are similar to trigonal bipyramid, but this is just a single pyramid. Any questions? So you look at the Lewis structure, you identify the number of electron groups on the central atom. Then you think about, well, what shape would the balloons make? We've got linear, trigonal planar, tetrahedral, trigonal bipyramid, and octahedral. 2, 3, 4, 5, 6. If there are lone pairs, pretend that those are invisible balloons and name what's left. So those lone pairs are actually more repulsive than the bonding pairs. And one way to explain this is that they spread out more in space. So here is a bonding pair of electrons, and they are stuck between the 2 nuclei of the atoms that they're bonded to, that they're bonding. Here we have a nucleus with a lone pair. This other end of that lone pair does not have to get squished down to fit between another nucleus. So it can spread out. And so you can see that this guy is going to take up more space than that guy around the central atom. So if we look at nitrogen, or ammonia here, the ideal geometry for a tetrahedron would have equal angles, all 109.5. But because there's a lone pair and it's extra repulsive, it's going to push the atoms a little bit closer together. They're going to be at 107 degrees. You do not need to memorize 107 degrees. You should remember 109.5. The lone pair, what I expect you to be able to tell me is that this angle is less than 109.5. Okay? It's going to push the other guys together. Any questions? Let's look at water. Lewis structure for water. oxygen and 2 hydrogens, and then there's lone pairs. And that's how we typically draw water Lewis structure, in a line, right? When we look at the central atom, though, how many electron groups are there? 4. 4 groups makes a tetrahedron. So here is the 4 groups making a tetrahedron. This is the geometry of the electron groups. So there's a lone pair here and a lone pair here. They're definitely taking up space, and so they're pushing those hydrogens together. To identify the molecular geometry, we're going to pretend that the lone pairs are invisible. So I'm just going to make them disappear. And so then what do we have left? Well, that's not linear. It's not triangular. Very fancy. It's bent. Okay? That's a bent structure. And again, the angles are affected. So perfect tetrahedron, angles would be 109.5. Here with water, we have 2 lone pairs, as opposed to ammonia's 1 lone pair. And so the bond angle between the atoms is going to get even less. There it's 104.5. Any questions? Relative repulsion of electron groups. So lone pairs next to lone pairs, that's the most repulsive. Lone pairs next to bonding pairs is the next repulsive, and then bonding pairs with each other is the least repulsive. So the number of lone pairs on your central atom is going to affect the bond angles. So here on methane, there are no lone pairs, and so we have a perfect tetrahedron. Ammonia has 1 lone pair up here, which pushes these guys a little closer together, 107. And water has 2 lone pairs, and so that pushes these guys even more together. What is the molecular geometry of a molecule whose central atom has 3 bonding groups and 1 lone pair? So let's just, you can do this in your head, but I'm going to do it on the screen here. So here's my central atom, and it says it has 3 bonding groups. Okay, so that might be 3 bonds, right? And 1 lone pair. And a lone pair. So how many groups is that? 4 groups. What is the electron geometry of 4 groups? Tetrahedron. Okay? You have to look at the electron geometry first. So the electron geometry, well, we sometimes abbreviate that, e.g., electron geometry. So the electron geometry is a tetrahedron. And then we imagine that tetrahedron with the 4 balloons. We have 1 lone pair. The lone pair is an invisible balloon. What's the name of that shape? Trigonal pyramid. So the molecular geometry is going to be a trigonal pyramid. So that would be letter D. Any questions? Five electron groups with lone pairs. So the Lewis structure for SF4 And if you go through the steps, you should end up with this shape. We gave everybody an octet, and we still had an extra pair of electrons. Sulfur's in period 3. It's big enough to expand its octet, and so we'll put the lone pair on the sulfur. So we have 5 electron groups, right? So the electron geometry is the bipyramid, trigonal bipyramid. So here's the trigonal bipyramid. In the trigonal bipyramid, there are 2 different types of positions. There's the axial position and there's the equatorial position. And the lone pair is more repulsive, right? So it wants to be in the place where it has the most space. This axial position is not where it has the most space because here it has 90-degree angles with 3 bonding pairs. When we put it in the equatorial position, now it has 90-degree angles with 2 bonding pairs and 120-degree angles with the other 2. So there's more space. So it's a trigonal bipyramid electron geometry, and then when we make this lone pair invisible, we get this shape. And I'll show you with the model kit why we call that. So here's our trigonal bipyramid, right? And if we make one of these a lone pair, like it's invisible, this is what we have left. And it's like a little teeter-totter. So that's called seesaw. I don't know why there's no fancier word for it, but hopefully everybody knows what a seesaw is, a teeter-totter, right? So that's what this is, a little teeter-totter. So that's a seesaw geometry. Any questions? Well, if we have 5 electron groups with 2 lone pairs, that would be something like this, bromine trifluoride. We have 2 electron groups. Those lone pairs have to go along the equatorial part so that they have the most space. So we get the trigonal bipyramid electron geometry. We pretend that these are invisible, and we look at what we have left. And what we have left is a T shape, right? It looks like a T. Fancy, fancy. We've got the trigonal bipyramid, and then we have seesaws and T's and bent. I don't know. Let's just be thankful they didn't come up with something more complicated. Xenon difluoride. This guy's like almost all lone pairs, right? So there's 3 lone pairs and 2 single bonds. So a total of 5 electron groups. So again, we have this trigonal bipyramid structure. The lone pairs are going to go along the equator. And so now when we look at this, all we see are the atoms in the equatorial positions. And so that's linear. We also saw linear if we only had 2 electron groups. But you can get linear with 5 electron groups also. Any questions?
So is that always going to happen with like the whole space thing? That we just create the equatorial?
Yes, the lone pairs will take the equatorial positions because there's more space. So you can imagine the balloons. Now, I added one, so this is an octahedron. But if I had 2 small balloons and 3 big balloons, the big balloons would go around the equator, and the smaller balloons would be on the top and the bottom. That's how it would fit the best. Six electron groups. So bromine trifluoride. We've got 5 bonds and a lone pair. So a total of 6 groups. 6 groups makes an octahedron. So here we have our octahedron. All the bond angles are 90 degrees, so there's no special positions. We make one of these invisible, and we get square planar. I'm leaving this guy, that's the lone pair. Also makes a nice handle. So, I'm sorry, not square planar, square pyramidal. So there's a square at the bottom, and it comes up to the point at the top like a pyramid. Square pyramidal, or square pyramid. Xenon tetrafluoride. Looking at the Lewis structure, we have 6 groups still, but now 2 lone pairs. So lone pairs next to lone pairs is not happy because they're both big and puffy and take up a lot of space. So because of that, the other lone pair will be on the opposite side. So when we take that shape and remove the top and bottom, what we have is a square, and it's flat. So this is square planar. It's a square that's in a plane, as opposed to the previous one that was a pyramid with a square bottom. So that's on the screen, a little too small to read, but that's a table from your textbook that basically summarizes everything we've talked about so far. And if that table is useful to you, I encourage you to use it. But I think the best way to answer these questions about shapes is count the electron groups, think about how the balloons would get away from each other, and then any lone pairs, make them invisible and describe what's left. Here's a question about lone pair repulsions. Imagine that a molecule with 6 electron groups is confined to 2 dimensions and therefore has a hexagonal planar electron geometry. If 2 of the 6 groups are lone pairs, where are they located? So this one's flat because they're saying it is. So our choices here are all involve number 1. So this is a lone pair. Where's the other lone pair going to be? It's going to be on the opposite side. It's going to be over here, so that they can get away from each other as much as possible. They're less repelled by these bonding pairs. So they're like, well, I'd rather be close to you guys. I really, really don't want to be close to him, right? Very, very repulsive. So that would be letters C, 1 and 4. And that's one of those questions where that's not a reality-based question, but the question addresses, do you actually understand what's going on, or did you just memorize something else? So this is a summary of VSEPR theory. The geometry is determined by the number of electron groups, which you get from the Lewis structure. An electron group is a lone pair, a single bond, a double bond, a triple bond, or single electron. The geometry of the electron groups is determined by their repulsions, and then bond angles can vary because lone pairs are bulkier, and also multiple bonds are bulkier than single bonds. So that's a good summary slide. Which statement is always true? That's always kind of a dangerous thing. Always and never. The shape of a molecule is determined only by repulsions among bonding electron groups. The shape of a molecule is determined only by repulsions among non-bonding groups. Let's highlight these differences. So this is repulsions among bonding electron groups, and this is non-bonding electron groups. The shape of molecule is determined by the polarity of its bonds. Well, that didn't go very straight. Or the shape of the molecule is determined by repulsions among all electron groups on the central atom or interior atoms if there's more than one. So this is talking about repulsions among all electron groups. It'll be D. Bonding groups repel each other, and non-bonding groups repel each other. But we can have both of them in the same molecule, and they both matter, and so letter D is the correct answer. All the electron groups.